Good afternoon, everyone. How design can actually play a big role when it comes to cooling loads. As a sustainability and building performance consultancy, our work is helping developers, architects, and owners design buildings that stay comfortable while using far less energy. And there's one idea underneath everything that we do, and that's the one that I'm going to try and share with you today. So it starts with an instinct that we all share. Typically, when a room is too hot, we reach for a bigger air conditioner. And when a building overheats, we specify a bigger chiller and try to make it cooler through larger and larger systems. So for the next 10 minutes, I want to make the case that this instinct where sizing the machine to solve a problem is actually almost the other way around. It's backwards. And the most energy efficient and the most comfortable buildings, which also Mr. Jagjeet shared some examples of, are where it didn't start with the system, but rather started by needing less from the systems. And so over the 13 years now through Green Grid Designs and Building Energy India, I've seen the same pattern across residential towers, mixed-use development, schools, township scale, master plan projects even. A building's thermal comfort is largely decided even before a single duct is ever drawn. So let me take you through how we approach it and show you with a few callbacks to examples of projects which I've done about how this plays out. So number one, designing the load out first. So if we're able to design the load out as much as possible and through design remove as much load as possible, then we're able to achieve a lot right at the outset. So every building has a cooling load, which is the amount of heat we have to remove to keep people inside the building comfortable. And here is the crucial part, that load is set by decisions made long before the HVAC engineer even arrives on the scene. Orientation of the building, window to wall ratios, the glass specifications, shading, insulation, the envelope, the entire building envelope, right? All of these have a huge impact on what we actually consume as energy at the end of the building construction and the building design. So in a hot climate, the envelope is doing the heavy lifting. Whether we design it to or not, the maximum heavy lifting is the envelope. And if we get it wrong, then we spend the building's entire life paying for that wrong design or that wrong decision through electricity, right? And if we get it right and we shrink the problem before we ever try to solve it mechanically, right, then we're able to save that much energy through the entire building's life. So at Green Grid Designs, this is where our work begins. This is where we work on how to remove the load, not through equipment. Right. So let me make that a little more concrete. On a 35-story mixed-use tower in Mumbai, we treated the facade as an energy system, not a finishing or just a facade. We ran the whole building through energy modeling, through radiation analysis, through wind and CFD studies to tune the shading geometry and glass specification, the orientation of each facade one by one, and achieved something where we were able to get a higher performance glazing. We were able to use ways to remove the solar load at the worst times of the year, and ensuring that there was openness where it was safe on the safer sides and bringing more ventilation cooling. And so using this kind of a layered method in solar shading and of course using on-site renewables as well, our overall result was a 28% reduction in energy performance index and a 22% saving in the HVAC load. And that 22% is capacity we never had to buy, or we never had to power it, or we never had to maintain it. This was 22% just clean off right from the beginning, right? So this is the cheapest kilowatt in any building, which you can design out right from the start. So that was one. The second thing is about the envelope and the HVAC and understanding how these two are actually one single system and they operate together. They respond to each other. So this brings me to my second point, which is it's really the heart of thermal management, the envelope and the mechanical system are not two projects, but one singular system, and they have to be designed as a conversation. So the conflict we run into is usually not technical, it's organizational. The architecture gets finalized, and then the MEP engineer comes in and is handed a finished building and is told that, you now have to make it comfortable. So with no other option, the safe move is to size for the worst case. But when we're talking about, when you're trying to address oversized systems, when you're trying to address, systems with which have these extra safety margins, etc., we need to understand that it's short cycles, it controls humidity poorly, and it costs more to install and to run throughout the life cycle. So when we are approaching a project, we try to address this issue right from the beginning. We say that it's important to bring in the energy modeling right from the outset, do some daylight analysis, do some CFD into the design, while the geometry is still moving, while there's still space to actually incorporate changes, and the facade and the plant are then tuned to each other, right? So the cooling system and the facade work together. On another project, this was a 19-story mall and hotel building. We did the sequence in the right order. We modeled the envelope and the daylight first to bring the peak cooling load down, and only then the HVAC to that reduced load. So rather than to the worst case guess, pairing that right sizing with the daylight autonomy, which also trimmed the lighting load, delivered an overall 24% energy reduction, right? So better thermal comfort also at the same time, and also other energy savings through that process. So right sizing isn't about doing less. It's about matching the system and the machine to a problem we've already made smaller through the design of the building, right? So this was my second point. Now the third point is about fresh air without the energy penalty. So there's a genuine tension at the center of all this, and I don't want to gloss over it. The tension is between energy and air quality. We can make a building airtight and efficient, but people need fresh outdoor air to stay healthy, alert, and well, right? So in a hot climate, conditioning that incoming outdoor air is expensive. That's where we end up spending a lot because we're bringing in hot outdoor air. So, since the pandemic, none of us are willing to compromise on indoor air quality, and of course, rightly so. So, how do we ventilate properly without throwing away the efficiency that we just worked so hard to build? So, our answer is to stop treating ventilation as a blunt instrument and just bringing in fresh air. Use the heat recovery ventilation. Let us capture energy from the air that we're exhausting and use it to precondition the air that we're bringing in. Occupancy-based zoning, demand control ventilation means we condition where people actually are specifically and when they're actually there, not the whole building at the same time all the time, right? And automated controls let the building respond to all of these kinds of dynamic variations in real time. So a good example is where we had a school which we were working on, the Orchid International School in Mumbai, and classrooms were extremely unforgiving. It was extremely hot, and at the same time, you have to have daylight without giving glare, right? We also needed fresh air without the heat. So these were some dualities which we struggled with. And what we did is we designed daylight first, and then we tuned in the window wall ratio and the shading depth for each of the classrooms, controlling the glare, cutting the roof heat that was coming in, and then added a mixed mode ventilation strategy that used not only natural ventilation when conditions allowed it, but also the mechanical cooling and the air conditioning as well. So the cooling hours automatically dropped by 30%, while daylight and classroom comfort improved. The children got better air and better light, and the building used less energy. So that's the kind of equilibrium that we're aiming for, comfort and health going up and energy coming down at the same time. So, so that was my third point. And the fourth point is about how we let data lead and design for the climate that's coming in the future. So this last point is about how we make these decisions with confidence. And it's this, at Greenwood Designs, simulation-based analysis is not just about a compliance tick box, just to be done at the end somehow. But it's rather how do we change the way we design? And when we model energy, daylight, airflow, and thermal comfort early in the design process, we're not just proving a building passes a rating, we're testing ideas before they're too expensive to change, right? And that's where everyone saves a lot of time, a lot of money, and the whole building's life is actually a big saving when you're able to do it right as well. So right, so testing these ideas before they're too expensive and benchmarking the performance so we can keep improving it even after handover. Right. So, on a campus expansion for the Tibetan Institute in the Himalayas, we developed a heat harvesting strategy, the opposite way around, designing to hold warmth in a cold climate, which proves the method works at both extremes. We used thermal mass and local stone in place of brick. We angled the window projections to catch the northwest sun, right, and got some heat coming in from the north as well, and not just from the south side. And we validated the ventilative cooling through CFD. So daylight autonomy rose to 62%, and all of it was decided and proven in the model before anyone even broke ground for foundations, right? So here's why this matters more and more every year. A climate, the climate a building is going to live in is not the climate that we're designing for today. Right now, we have numbers and data, which very often our analyses are even based on numbers from before. But we know that the climate has already shifted. There are already changes happening, and we're predictably now looking at what's going to happen in the next 10 years as well. Cooling demand is rising. A building we complete today has to stay comfortable and stay efficient for the next 30 years. So we have to design for the climate that is in the future and not just the one on the drawing today. When we lead with data, net zero stops being a slogan and becomes an actual practical calculation, an incremental pathway which shows how the building, the envelope, the systems which are right sized, the ventilation, intelligence, and also the performance overall becomes measured. It becomes tangible and it becomes an actual number which we can then work with. So let me close with this. Bringing it back to where I started, thermal management is not about a bigger air conditioner. It's a sequence. Reduce the load first through the envelope, design the envelope and the systems as one conversation, protect the air quality intelligently and not wastefully, and let data lead every step of the way. That sequence is exactly the work we do at Green Grid Designs, sustainability at all scales from single classroom up to a whole master plan. The question our industry is really facing is not whether we can afford to build this way. As climate demands rise, it's whether we can afford not to design this way. So thank you, and I'm looking forward to the discussion.